Hi, I'm Thomas. I'm working at Synervoz with a team of audio developers. Our day-to-day work is to iron out issues with audio engines, optimize performance, and generally getting audio applications to run correctly in the right place without pops and clicks. We've been making a tool for audio developers to navigate the ever-changing world of audio development across multiple platforms. And now is a good time to share progress. As audio application developers, we find some recurring problems when it comes to prototyping, evaluating, and deploying the kind of complex audio pipelines that are required in modern applications. As the audience's technology expectations grow and functionality gets more complex, it's very common for developers to pick the best tools for the job from an ever-increasing selection of libraries. One audio library rarely ticks all of the boxes, and additionally, each library might go about things in a slightly different way. Initially, there could be some differences in the way that a library is loaded and bundled, which can often be troublesome enough as it is. Then there may be differences in the way settings are changed and their APIs are called. Audio assets may be passed around differently. Maybe the buffers passed in and out of the effect are different sizes, sample rates, formats, or shapes. Maybe it's also foolish to assume that a non-audio developer knows what these audio domain concepts such as sample rate and audio buffers even are. At Synervoz, we're often asked to fix audio pops and dropouts in performance, port an audio engine between platforms, develop UIs, and deliver production-grade audio. So, we've built a platform and SDK that helps to streamline the audio pipeline development all the way from prototyping to production across multiple platforms. So let's take a look at a simple example. Let's say a software developer wants to create the following audio pipeline prototype for a client. The developer may or may not be an audio developer. Both flavors of developer will appreciate the simplicity gained with the SDK here though. The application takes the user's microphone signal. It then passes the audio signal through a high-pass filter to remove low-frequency hum, then passes the signal through some dynamics compression to even out the loudness and raise the overall perceived volume. Finally, the processed audio is sent to the user's headphones. Let's think about what we might have to consider when building this from scratch. As you can imagine, recurring complexities start to appear time and time again. Do we need to set up the audio engine again from scratch? How do we access the device's microphone? How do we make sure that when we do access the microphone that we get a clean signal without any platform-specific processing being applied? Do we know which libraries we want to use yet for the effects required? All audio libraries will sound slightly different. They also have different ways to set them up and control them. Will these libraries be easy to stitch together? Will we need to think about multiple threads to process the audio efficiently? Might the client maybe add some more requirements later on that might not be possible with the particular libraries that we've decided on? How do we avoid being stuck into one vendor's design pattern? While developing the audio pipeline, we might want some simple UI components to control the audio effects so that we can tweak the settings as we hear them. Making UI components like this can be an absolute can of worms alone. After many years of facing similar problems, an elegant solution has naturally emerged. We've developed the Switchboard Audio IDE, a tool for prototypers, developers, and product designers to develop reliable audio engines. Cross-platform audio graphs are defined in the JSON format with no code, allowing to focus on what's connected where and how it sounds, leaving the rest to us to handle. Choose from a range of node types to build complex audio graphs that keep up with modern application functionality. Preview the audio engine on the fly instantly. In the process, know exactly where your pipeline will be able to run and which platform is supported. We split the task of developing audio pipelines into 3 distinct parts: the design, the evaluation, and the deployment. So let's have a look at how this works. Let's start with the designing of the audio graph. As mentioned, we define our audio graphs with simple JSON. We can populate the nodes in our JSON using a useful node browser in the UI. Here, we are defining the 2 node types in this audio engine: a source node which takes the user's clean audio input from the microphone, and a dynamics compressor node from the WebAudio namespace. Click Run JSON and you'll be shown a fully configured audio engine. Put some headphones on and preview the way the nodes sound and tweak the parameters with the built-in UI controls. Let's say, for example, that we want to change the vendor of the second node, which we have defined as a dynamics compressor. This is currently using the WebAudio namespace. This compressor may be fine, but let's say we wanted to potentially run our audio engine on native platforms too, where the web audio is not available. For that, we'd need to use a cross-platform vendor instead. Here we've switched the web audio compressor for a similar audio effect from the superpowered library, which is a third-party audio SDK. The superpowered compressor does sound quite different to the stock web audio compressor. In fact, it sounds pretty good. Normally in this scenario, to use or even test the compressor component above using the superpowered SDK would usually require the developer to host the library files possibly and know how to include them in their application, write audio workload scripts if on the web, or understand how to call process loops, pass parameter changes across threads, and also know the logical bounds of each parameter, say for example the threshold or the knee, so that the UI components can be built. We skip over all of that. The node is instantly replaced and everything is wired up for you automatically by simply changing the JSON. The Switchboard Audio IDE provides you with various other tools to help you evaluate the audio graph. Here we can see exactly which platforms our JSON graph will be running on under the text editor on the left. We can visually check for output peaking and adjust parameters accordingly. During this design and evaluation stage, Switchboard JSON graphs are run in any browser on any device. Maybe we're also working in a team for a client, and we'd like to share our audio pipeline amongst other developers or maybe even the customer so they can see how things sound before we make any commitments to libraries. With a public URL, any device can load the exact same setup with the exact same audio engine. Desktop, tablet, and mobile are all supported. Mobile support is particularly useful because the microphone arrangements on mobile phones are often quite different to that on laptops. So it's useful to hear what the same audio graph will sound like on different devices. Let's take a more realistic and advanced pipeline and follow the process through the Switchboard Audio IDE. Imagine we're working with a client who is building a vocal performance application where they can share their performances. Here we see that the audio is passed through more processors before being sent to the headphones. In this example, we're also going to replace the user microphone with a pre-recorded singing sample to make accurate and repeatable audio evaluation possible. We'll need more nodes to make this work, but the concepts are all the same. Here you'll notice a few things. First of all, we're mixing many different libraries in this graph, which really highlights the simplicity of working with the Switchboard SDK. Here we're using nodes from the standard Web Audio API and also two third-party library vendors, Superpowered and RN Noise, both excellent in their own regards. You'll also notice that we're defining audio assets at the bottom of the graph under the tracks property highlighted in yellow. Here we're instructing the graph node with the ID audio player to load the given URL, also highlighted in yellow. Lastly, you'll notice on the right that I've included a portrait screenshot of the graph. This again is the mobile view. It rearranges the graph and automatically lays it out from top to bottom rather than left and right. So let's say we want to change a part of the chain, just one particular node in the chain. So this node that we'd like to replace is the reverb node, which is the last node in the chain. We'd like to reload this and evaluate two different nodes side by side, but without reloading the entire graph. So you may have heard of a particularly nice sounding reverb called Freeverb. So if we look around on the web, we'll see that Freeverb is actually available as a free piece of Faust code. So wouldn't it be nice to have a Freeverb running alongside the existing superpowered reverb and toggle between the two effects on the fly so we can perform a comparison of how they sound? How it sounds is, of course, the most important factor, right? Something important to note here is the node directly before the reverb node, which is, in this particular graph, is the superpowered echo node in this particular example. We'll introduce two new features of the Audio IDE here. First, we'll be using a new node called the source switcher node. This essentially facilitates A/Bing, which is toggling between two sources instantaneously to make comparisons. Here we also let the SDK know that we need two input buses with the num inputs property in the node configuration. In order to connect up the source switcher node correctly, we need to introduce the second new feature, connections. So previously in the examples I've shown before, the nodes were simply connected in series. Each output of a node was connected to the input of the next node in the nodes array until the last node, where it was automatically connected to the speakers. We need to do something a little different now. We need to have a graph where the output of the superpowered echoed node now needs to get fed into two separate stereo input buses of the new source switcher node. The single stereo output of the source switcher node needs to be connected to the speakers. To do this, we'll need to define some connections. When connections are defined, the automatic connection of node in series is not performed by the audio engine, and each connection must be defined manually. This gives us a lot more control of how things are connected up. Notice that I've curtailed the list of both the other nodes and connections of the large graph to keep the example here just a little neater. First, we'll connect the output from the superpowered echo node to the input of the superpowered reverb node, both highlighted in green, with the connection highlighted in yellow. You'll see that we're simply referencing the nodes by ID here, which is a property that we give the node in the JSON. We then continue to connect the same output of the superpowered echo node with the input of also the Faust reverb node, highlighted in yellow. We'll then create two more connections. The first connection is between the superpowered reverb output to the first input of the source switcher node, our new node. The second connection is between the Faust reverb output to the second input of the source switcher node. These are listed as buses by index. On the right, you can see the source switcher node in action and its associated connections. Use the slider to instantly jump between the two reverb effects. It's worth mentioning that the slider here will snap from A to B. It does not mix the two signals gradually. If you would, however, prefer to mix the two signals, a similar connection approach could be applied to a mixer node instead, which is also available in the node browser. This may be useful in some cases. Although we won't cover them in this presentation, there are some other useful features that we can be defined in the JSON. We're also able to define presets of parameters, which can be easily saved and switched. Although a silly example in this case, which just changes the volume of a sine tone, it can be used on as many parameters as you like across many nodes, all in sync simultaneously. This allows us to quickly switch between presets that will dramatically change the sound of our audio graph. These again will be included in the audio graph if the audio graph was to be shared. So let's look at some more extensions that are available, which is what we are calling namespaces in the JSON. So WebRTC is an interesting node type. WebRTC allows near real-time communication over the web through standardized browser APIs. Agora is one of many popular managed providers in the WebRTC industry. With the Agora Sync and the Agora Source nodes, we can broadcast and receive remote audio streams, but with just two lines of node configuration in the Switchboard SDK. So just supply the room name and the peer IDs and add them to your JSON graph just like you would with any other node. Create two different JSON graphs, which can be auditioned across two different machines by sharing the audio graph URLs. This way you can both audition audio pipelines at both ends of a WebRTC call in a way that's fully isolated from your main application development and all of the associated complexities with that and sharing that, and just focuses on the audio pipeline aspect of your application. We're also currently working on the creation of a new Switchboard peer.js extension, which will enable true peer-to-peer WebRTC, removing any of the associated cost with using WebRTC infrastructure, such as those provided by Agora. Maybe you would like to perform some speech-to-text transcription at some point in our audio graph. The text transcription could then be consumed and used elsewhere in our application outside of the audio pipeline. Pico Voice offers client-side AI-powered speech-to-text transcription with no external dependencies or remote server calls. Pico Voice Cheetah was a particularly tricky library to get set up, and there were no working examples in their own documentation of how to supply Pico Voice with your own custom audio feed rather than the user microphone feed on the device. So under the hood, the audio signal that we pass in must first be converted into mono, then resampled in a separate audio thread to 16 kilohertz, then finally converted from float buffers to int buffers until Pico Voice can actually process the signal and produce the transcription. The Switchboard SDK takes care of all of this for you behind the scenes, allowing you to quickly drop it in and test its performance by simply dragging the node into the JSON. Web audio modules, or WAMs, are a standard way of distributing web audio-based DSP and UI into convenient modules which can be pulled in from local or remote sources. Again, just apply the asset URL and we'll handle the rest of getting that hooked in correctly. C Major is another audio programming language that comes with a bunch of useful DSP utilities which you might find useful. It'll run on all platforms, although it's worth mentioning here that when deploying, we're only actually concerned with the audio processing aspects of the C Major library, not the UI. But it is useful to use the UI supplied by C Major here to set the parameters when auditioning. If you wanted to use the UI in your own application, you would still be able to do that. It's just we are only really concerned with the audio processing side, but we do expose that for you to get access to. Faust is another audio domain specific DSP programming language. They also have a built-in library to render the UIs. Here we're supplying the URL to a remotely hosted Faust DSP file. This could be hosted anywhere and is pulled in at runtime. The Faust.dsp code contains all the information to perform the DSP and also render the UI that you see on the right. Once you're happy with your audio graph after the design and evaluation stages, it's time to get your audio pipeline integrated into an app with the development stage. Notice along the bottom the compatibility matrix. Here you can see that this particular speech-to-text audio graph, which we've designed, is compatible with all platforms apart from embedded devices. The Switchboard SDK is available in most popular languages to get your audio engines up and running really easily. We currently have libraries for JavaScript, C++, Swift, Kotlin, Java, but for this particular example, we're going to show you how to get the audio engine up and running on the web in JavaScript. We aim to make this code as simple as possible with the Switchboard SDK. Here you can see we simply use the JSON which we defined in the audio IDE to create a new audio engine. Once we have the audio engine instance, we can start it with a function call and begin audio processing. Often these two steps above alone are enough, but you can also use the Switchboard SDK to select nodes in the graph, individual nodes within the graph for additional functionality such as setting parameters with code or actually accessing the underlying nodes APIs if they're provided by the vendor. So in this example, here we get the latest example from the Pico Voice Cheetah node as text, which can be used elsewhere in our application. And then for the example, we then set a parameter on that node to disable a speech-to-text transcription from that point onwards. There are some other notable features that we've been working on to further improve the SDK and the tooling around it. We're in the process of making the UI around the Switchboard Audio IDE a lot more of a drag and drop experience. We imagine dropping in new nodes and connecting audio connectors between nodes by dragging lines between the nodes with the mouse. Real-time ML inference, which will allow you to perform real-time transformations using machine learning, can be applied to audio signals with ML nodes. audio recording nodes, which will allow you to record to disk and or offer up downloads in various audio formats. We're also looking to implement the URL shortening. So currently, when you share a graph, the full JSON is encoded in the URL, which can be quite lengthy. So we're looking to provide a shortener for that by storing the JSON graphs remotely on the web and then referencing them by ID. We're also working out the licensing terms for the SDK, with effort going into both a one-off upfront cost or alternatively a pay-per-minute model, which is something that we would also like to explore with third-party extension providers. So yeah, we're not trying to write another audio library here. What we're actually trying to do is get the ones that already exist to play nicely together. So if you've written an audio library, we can help you monetize it by allowing developers to drop your modules into much larger audio graphs. We're very close to releasing extension templates to give third-party developers the means to get their libraries into this ecosystem. The library wrappers that we've made, some of them currently, they're only 20 lines of code, so they can be quite lean. It depends a lot on the complexities of your library and how people interact with it. Most importantly, have a go. If you're a developer looking for a simple and easy audio developing tool, or if you're looking for a solution to get audio engines reliably into production, we think the Switchboard SDK and its audio IDE can help you. We offer the design, playback, and sharing of graphs for free, and hope that is a useful tool for many developers out there just to see what's possible on different platforms alone. But when it comes to deploying the JSON in a hassle-free and unified way across platforms and languages, then that's when the Switchboard SDK comes in. We're still ironing out the licensing terms, and we're very flexible with arrangements during these early stages. So please get in touch with Synervoz to start a discussion. So thank you for your time. Like I say, please have a look at the doc site, have a hunt around the documentation, and there's lots of examples as well on the web. If you click the examples drop down at the top of the audio IDE, you can see lots of different libraries kind of playing nicely together, and lots of kind of interesting examples. So yeah, please have a go, and thank you for your time.